Hello everyone, I'm Minghua Cao, a PhD student from Loughborough University in the UK, supervised by Professor Vadim Silberschmidt and Dr. Konstantinos Baxevanakis. Today, I would like to present the part of the work from my research group, and the topic is about the effect of thermal expansion mismatch on the thermomechanical behaviors of compacted graphite iron. The cast iron, also compacted graphite iron, has already been widely used in the automotive engineering with good thermal and mechanical properties and a competitive price. And its working condition is mainly about high temperatures and high pressures. So in the microstructure level of the compacted graphite iron, we can see in the SEM images the black particles are the graphite inclusions inside. They are classified by their microstructure by the flake graphite and vermicular graphite and nodular graphite. And the green region as a metallic matrix consists of ferrite or pearlite or the combination of these. The ferrite is a soft and ductile phase with body-centered cubic matrix microstructure. And pearlite consists, it is a harder microstructure, consists of alternating layers of ferrite or cementite. And at their microstructure level, the fracture mechanism, their main fracture mechanism of compacted graphite iron is the debonding. They are interface debonding inside of the graphite inclusions or the interface debonding between the graphite and the matrix, or the interlaminar debonding inside of the graphite inclusions. My research is mainly talk about the interfacial debonding of the graphite from the matrix. Now, under the high temperature application in automotive engines and the cylinder head, the compacted graphite iron will meet the high temperatures, and their main fracture mechanism will be from the mismatch of thermal coefficients between the graphite and the matrix phase. And this interfacial debonding will cause the micro crack and then the micro crack, and then will be the mainly fear in the compacted graphite iron. So this is the initial stage of the damage. And the graphite particles is soft but brittle inclusions, and it's very easily to be debonded from matrix. So initially, researchers will model the graphite as the voids, and then it will be regarded as a rigid particles. And here is the representative volume elements as the united cell. This can represent the microstructure of the cast irons. For the spherical cast irons, there all the graphite inclusions were the sapphire, so it's easy to be modeled as a node. But in the compacted graphite iron, we have a little bit more complicated microstructure. So my research based on some microstructure characterization from 20 SEM images and the analysis by the image software, and can get the microstructure summary of the compacted graphite iron. I also have some assumptions. The sapphire graphite was a nodule, and the vermicular graphite I built a model is as the oblate sapphirate in 3D. The matrix will be the cube. Because there is a considerable spread of the data available in carbon and mechanical properties of compacted graphite iron, because different microstructure will give the different mechanical properties inside. So I selected 3 different types of the matrix. The ferrite matrix on the left-hand side, the ferrite matrix and the pearlite matrix based on the literature review, and the matrix was the effective properties of the matrix was from my in-house mechanical testing. The graphite inclusions was also, this is the soft but brittle material, here is the stress strain curve for that. On the right hand side is different coefficients of thermal expansion. We can see on the upper three curves, they are the metrics, and the graphite is at the lower level. They are so here the matrix coefficients of thermal expansion is 10 times larger than the graphite. So the matrix will expand significantly than the graphite influence. And for the damage law, I used a ductile damage criterion for the graphite influence to limit its response to the elastic region. And the damage will be initiated when the plastic region and the plastic strain for the grout occurred. And then when the damage becomes to one, the element in graphite will be removed, and then the graphite can't carry any load and be regarded as damage. Then this curve will be graded to 0. For the boundary and the loading conditions, I use the high temperatures and pure thermal loadings from room temperature to 500 Celsius and cooling back down. So this heating stage and the cooling stage. For the boundary conditions, I use the for the first side surface, there is the periodic boundary conditions and let the pair of nodes on the corresponding surface can have the same displacement but in the opposite directions. The free top surface and let both graphite and matrix to expand or shrink freely. Bottom surface, I will use some constraint and can let the nodes on the bottom surface can expand freely in the XY plan. And yes, this is the research what we showed in the last conference is the single graphite inclusions was embedded in the cubic matrix, and with two different periodic boundary conditions and fully fixed boundary conditions for all 6 surfaces of the cubic matrix for comparison. And use the linear thermal loading from room temperatures to 500 Celsius. Now here is the results example is the evolution of graphite damage developed and to affected by the graphite microstructures. So in this research, today I would like to introduce another type of the models is the half of the full cubic unit cell. So here, the graphite influence and matrix, they have the same levels of the displacement at the beginning. I use the nodular graphite and the vermicular graphite with the same volume fraction, just a different direction. Here, I call it VV is the major axis of vermicular graphite is vertical to the top surface. And another one is parallel to the surface, matrix surface. And I have 4 different models. For A and B models, they have the same matrix properties, but different coefficients of thermal expansion in the graphites. And another type is about the BCD. They have the same constant coefficients of graphite influence, but with different matrix mechanical properties. And all my results will be was validated through the thermal experiments. It was done by the Alicona machine can scan the height and the surface profile of the compacted graphite ion. And if you're interested, I can show you later. And go back to my numerical research is I export the center of the graphite inclusion center to, this is the path to the center of the outer surface. And totally this corresponding to 0 to 50 micrometers. And here, about the location 7.5 micrometers, this is the interface between the graphite and matrix. As I mentioned previously, the ferrites in the red line, they they have the largest coefficient of thermal expansion and larger than the blue, the perlite, and the effective matrix. Both these two types of the united cells, the matrix expands higher and significantly than the graphites. And in that direction, vertical, this direction, because of the mesovermicular graphites, this is the major axis is parallel to the top surface. There is a larger volume of matrix. So this U3 in the Z axis, this will have a larger expansion in the U3 displacement. This is at the 500 Celsius. And after the temperature cooling down, there will be both of all my united cell will appear the shrinkage phenomenon. And also the large volume gives of the matrix give the higher U3 displacement in that axis direction. Here is a distribution of damage in graphite inclusion with the ferrite matrix as an example. At 500 Celsius and after cooling down 20 Celsius, we can see the damage accumulated, and the highest damage occurs in the nodular graphite because of it has the larger volume of the graphite, and will have the higher mismatch between the graphite and the matrix. And another resulting example is the effect of graphite coefficient thermal expansion. As I mentioned, the constant coefficient of thermal expansion in my research is higher and larger than the temperature coefficients of thermal expansion in graphite. However, because of lower coefficients in the graphite with the lower level, and it gives a larger mismatch between the graphite and matrix. So so they give the purple lines is larger than the green lines, and both the thermal step and the cooling step, we can also observe the damage accumulation. And then finally is about my conclusions. The volume fraction of the matrix is significantly larger than the graphite inclusions, and its larger coefficients of thermal expansion will give more significantly effect on the behaviors of constituents. And although the graphite inclusions has a smaller volume, but it can still affect the behavior of the entire constituents. So we can't easily to just regard the graphite inclusions as the voids. So that's all for my presentation. Thank you very much for the attention.